Hi, welcome to Earth Science Chapter 5. What we're going to be talking about today is sedimentary rocks. And so there's a number of different materials that we're going to be, or objectives that we're going to be covering. So let's get started with those. There we go. Today, the first thing that we're going to do is look at the different processes of weathering, which are going to break down any existing rock and make it a sedimentary bits of sediment. And then we're going to see how the sediments can form soils. And then finally, we're going to look at the different ways that sediments can get transported. And then we're going to look at the different types of sedimentary rocks. We're going to see how sedimentary structures are existed, see things like mudcracks and ripple marks and cross bedding. And then one of the things that we're going to be talking about are the sedimentary strata. Now, strata means layer, and we're going to look at some of these different sedimentary stratas. And then finally, we're going to look at some marine strata beneath the surface of the water, which form underneath the surface of the water. And then finally, we're going to talk about how these areas are now exposed. And every rock is going to tell a story. So, when we start looking at sedimentary rocks, the first thing that we're going to be looking at are these different types of sedimentary rocks. So here's a classic example of a sedimentary rock that was taken beneath the seafloor in the Mediterranean seafloor. So this drill ship is drilling down, and beneath the sediment on the ocean floor, we see a number of different piles of sedimentary rocks, or sedimentary strata. And so we see things like some plankton, some little drifting organisms that had shells that have become part of the soil, the sedimentary rocks. Then we're going to see some halite or gypsum and clay. And so we're going to see that halite and gypsum formed in a very different environment than beneath the ocean. They formed they formed as an ocean bed was drying out. And then we see some more plankton shells, and then we finally see so what your book calls the basement, and we'll see that this is the craton, or the sediment, the igneous rocks beneath the Earth's surface. So when we start looking at sediments, there's a number of different ways that we can classify sediments. The first way that we're going to look at classifying sediments are to look at the size of these sediments. And when we start looking at size, there's some very distinct boundaries here. The first one that we're going to be looking at are boulders, and you know those as things that are fairly large. Then we have things that are cobbles, about like that. About the size of 2.5 centimeters or so to 10 centimeters. Then we have things that are smaller than 2.5 centimeters, and those are things called pebbles. And then smaller than pebbles are, we're starting to look at some of these really finer grain materials that are going to be more difficult to see. So we've got sand, silt, and clay. And you can see the scales there is 1/16 of a millimeter to 2 millimeters for silt. You may seem that that's a really weird number. Why are we stopping at 1/16 of a millimeter? This is what our fingers are really adept at feeling, and that's why that number was chosen. Smaller than 1/16 of a millimeter to 256 of a millimeter, we have silt. Now, everybody on Earth is going to have a hard time seeing things that are smaller than 1/16 of a millimeter. So it's going to be really difficult to identify these individual grains without magnification, without a magnifying glass. And then we have, or a microscope. If we start looking at things that are smaller than 1/256 of a millimeter, these things are called clays. Now, when we start off with any existing sedimentary rock, or any existing rock, and wanting to break it into sediments, this is going to be done through a process known as weathering. Weathering is defined as the combination of processes that gradually modify or weaken rock when exposed to air, water, act just below or the Earth's surface. That's the textbook definition. My definition is things that break down rocks. I would also add ice in this example. And so when things get broken down, and there's a number of different ways that these rocks can get broken down. There's two main categories if we're starting to look at weathering. These are mechanical or physical weathering, and the second category is chemical processes. Now, when we start looking at mechanical rocks, the easy way to identify that it's a mechanical or a physical weathering is you're going to take big rocks and make them into small rocks. So you're going to have the exact same minerals in the big rock as you are in the smaller bits. When we start looking at chemical sedimentary rocks, we will recall that in the last chapter when we looked at minerals, minerals have a distinct chemical composition, and if we start altering these chemical compositions in this chemical process, you're going to make new minerals. Now, weathering occurs in a number of different ways. The first thing that physical weathering tends to attack are cracks, joints. A joint is a crack in the rock with no movement. If there was movement in it, we'd be calling it a fault. And so there's a number of different ways. And so your textbook has an image of a piece of granite that has some sheeting that has taken place. We have the other example that they give in the book is a layer of granite that has exfoliated. Now around here, we have some great examples around here in the mineral area, we have some great examples as well. One of the classic examples that when I was an undergraduate, I went to Elephant Rock. I was living and going to school in Eastern Illinois, and we came down to the mineral area because of one of the reasons was because of the great weathering exposures that we have here. Now, when we start looking at some of the different ways that we can take big rocks and make them into small rocks, or mechanical weathering, also called physical weathering, is to use some aspect of water. Now, in Missouri, we have multiple days that have cycles beneath freezing and above freezing. So you have this freeze, thaw, freeze, thaw, freeze, thaw. And this frost wedging is very, very good at getting inside little bits of rock, freezing, and when we all know that when water freezes, it expands in size. And so what's going to happen is going to go into those cracks or joints, and then it's going to freeze and break these rocks apart. Now, as it turns out, we're going to talk about this extensively throughout the semester, is rocks are really, really good in compression, but much weaker in tension and pulling apart. And so when we have water in a rock, in the pores of a rock freezing, it's going to be pulling the rock apart. And so we can actually see that this is a much, much weaker force on these rocks. And so these rocks tend to break. This is the same reason that earthquakes cause a lot of damage to rock-built structures or rock-like structures like brick or stone or concrete. It's the pulling apart that is the factor that causes rocks to not be as strong. And so frost wedging is doing the exact same thing. It's getting in those pores and it's pulling it apart. Another way that we can do this is by root wedging. Same process, different mechanism to break these rocks apart. And so this is an example of some rocks that have been pulled apart by plants. As the plants get in the rocks, what's going to happen, the plants get into the cracks of the rocks, the roots are going to grow, and the roots themselves growing is going to split apart these rocks. You may have seen some sidewalks where you've had some problems where these plants, these tree roots, will actually cause the concrete, kind of like a rock, to pull apart. We can also do this with salt. And salt water can get into those cracks, and those salt crystals can grow and pull these rocks apart. Some other examples around here that if you go to Elephant Rock, there's a great example of water getting into the individual cracks, or we have some granite around here that are some really great examples of granite. And this granite is very consistent, and it's called Missouri Red or Graniteville granite. And it has been shipped all over the United States to be used in things like monuments and buildings, buildings. And so if you were going to quarry this out, historically, what you would do would use a wedge. You would use a metal spike that would actually drive this rock apart, and you would slam down on the metal wedge, and it would pull these rocks apart. And then you have little braces in there. And nowadays we don't use hand sledges to pull these rocks apart. We use explosives. We still drill into the rock and put the explosive in the rock, and when the rock explodes, it's going to pull these rocks apart. So we have lots of examples of these wedging techniques, but in all these processes, you're pulling the rocks apart. Again, rocks are very strong in compression when compared to tension. Some other examples of how we can use this in our everyday lives. If you're going to look at trying to do some building, we would try to, if you were building with stone or brick or solid rock, you'd want to build as many arches over cavities as possible. Because if you had a flat surface, what's going to happen is that's going to cause the rocks underneath to bend or be under tension and break. But if you had an arch, what's going to happen is all those rocks are in compression, pushing on one another. And so since the rocks are much stronger in compression, this is a much stronger structure. But I think most people in Missouri, especially the eastern half of Missouri, are very familiar with the techniques of arches and the strength associated with them. Now, the second major category of weathering is chemical weathering. Now, as I mentioned, chemical weathering is going to involve, you start off with one mineral, you end up with a different mineral. And so this example in the slide is looking at what's happening where we have a water molecule attacking the surface of this crystal. And what's going to happen is the water is going to interact with the mineral itself, and will actually start to move atoms around to end up making different minerals. You'll notice that the image right here is contains, looks like this mineral, maybe this sample is a bit of halite or salt. Then the water is going to start to pull off different elements, and you're going to end up with potentially a different chemical concentration here, or it's going to just be a different shape. But these minerals typically are going to end up with a different chemical composition. Some classic examples that we look at around here in the mineral area are things like feldspars weathering into clay minerals. We don't have to rely exclusively on water, although water is a very common reaction that takes place, and we call this hydrolysis. Reactions that are going to use water to break down minerals. And again, it tends to attack surfaces, and if we attack surfaces, corners and edges have more surface area than the middle of this rock. And so what's going to happen is sharp edges are going to start to chemically weather away. One other technique that we can use to break down, change the mineral composition is oxidation. We know that the atmosphere is about 20% oxygen right now, and as a result, with the sea of oxygen, anytime we have iron-rich rocks near the Earth's surface, it's going to come in contact with this oxygen, and you're going to cause these rocks to oxidize or rust. Many times, if you look at a granite countertop, it looks a little different than if we were to look at some of the rocks at the elephants in Elephant Rock. And the Department of Natural Resources in Missouri has some great examples and great photographs of elephant rock. And these rocks are a little bit more dingy or weathered, chemically weathered. And so this is a kind of a 1-2 punch for breaking down rocks. Mechanical weathering is going to actually cause rocks to freeze and thaw, and that's going to cause some cracks to enlarge. It's also going to make new surfaces. Then we have chemical weathering attacking those surfaces. So we have rocks creating more surfaces, those surfaces getting broken down. And so what's going to happen is over time, these rocks are going to get smoother, rounded, more and more rounded. And so now we have some minerals that don't react very well to chemical weathering in some rocks. And a great example of this are little bits of quartz. And so we have this image of this granite here. It contains 3 different minerals in this example. It has some potassium feldspar, the pink mineral. The little black specks are little bits of biotite. And the white grayish colored samples are bits of quartz. Now I mentioned that feldspars are going to chemically weather to create these clay particulates. The biotite has iron in them, and the iron is going to oxidize or rust. And the byproduct of these minerals are going to be clay minerals of which can accumulate in here. But then we have the quartz. Now quartz, we learned, has a really low melting point in the last chapter on igneous rocks, but it is very, very, very stable at Earth's near the Earth's surface. And so as a result, it's not going to break down very easily. It's 7 on Mohs hardness scale, we learned, so it's really resistant to abrasion. It's quite strong. It's not going to allow water to get into those individual cracks and freeze it or thaw it. It's not going to chemically weather very easily. And as a result, when we start looking at materials further downhill, downstream, these quartz hold up really, really well. And as a result, we end up with a lot of beaches that are going to be rich in quartz. Now, since these rocks, layers of rock, are going to contain different minerals, they're going to weather differently. So in the example of your book, we have some shale, which are clay particles, which break apart very, very easily. And then we have some strong sandstone. Sandstone is a layer of rock that mainly is rich in, well, sand. And as a result, those sand particulates are going to be a little bit stronger, more resistant to weathering than some of these weak shales. And I do want to kind of point out some of these rocks at the top are pronounced, and some people may worry, are these rocks going to fall off? What we end up with is something called a balanced rock in this example, where the upper rock might end up starting to lean towards one side, but as a result, that rock that side is going to be under compression. If it's under compression, it's going to be stronger. And so the side that's not under that compression, is under tension, is going to weather faster. And so it'll balance itself out. And so it's not uncommon to get these rocks up at the top to be balanced. So here is the example of the 1-2 punch that I was just mentioning, where mechanical weathering is going to cause rocks to become more angular. Then the chemical weathering is going to start to round off these surfaces because, again, more surface area for chemical weathering to attack, it's going to weather 3 times faster. When we start looking at these sedimentary rocks, there's a number of different processes which can cause these sedimentary rocks these sediments to form sedimentary rocks. One of the ways is by taking these bits of sand and smashing them back, gluing them back together, or just pushing on them. All right. Those clay particles are really, really small. And so I kind of blew these clay particles up to be the size of poker chips. And so in my example here, these poker chips here, there's going to be some spots that are going to be under more pressure because they're going to be in contact. And as a result, this squeezing of materials together can actually cause these clay particles to form a sedimentary rock. And so that's one example. The other example that we can actually cause rocks to get glued together, and there's lots of gluing agents in nature. My best example that I can give is a popcorn ball or a Rice Krispie treat. And so where the sugar is, in fact, or the marshmallow is the cementing agent. And so we have these Puffs Rice cereal that are glued together with some form of sugar. And so we call this cementation. So both of these are going to form sedimentary rocks. And if, as it turns out, these sedimentary rocks can be, in those cases, are going to be called clastic sedimentary rocks. Then we have deposition sedimentary rocks, and these are commonly referred to as chemical sedimentary rocks. And the classic example that I give on this is a piece of rock candy, where you take sugar water and the sugar water will evaporate, leaving behind a super concentrated amount of ions in the water. The ions precipitate out to create rocks. And so some examples of this would be some halite or gypsum, and these are evaporating through, causing deposition of sedimentary rocks. Other examples would be coal. So since every rock tells a story, if we take a look at a rock, you can tell where and how this rock was formed. I have two sedimentary rocks, and I'll get some lighting on here. Hopefully that's a little bit better. These two bits of rock were both made up of bits of material that are now glued together. So the cement has occurred, and so these classic sedimentary rocks are going to tell us a story, and we can actually differentiate between these two stories. So this first sample is called breccia, and if you look at the chart here, it says that this is gravel that's been cemented together, but the pieces are very, very angular. Now we know that water is very, very effective at rounding off these samples, and so as a result, the breccia, we know that those pieces or clasts have not traveled very far from their source. There's a couple of different types of breccias. One type of breccia occurs right at where faults start grinding these rocks apart. So we have these little angular bits, and those bits of material get glued back together. This is a sample called fault breccia. This happens quite a bit in Italy. We know some of the earthquakes and faults associated with that area, and that's why this name is an Italian-sounding name, breccia. That's where the origin of that word came from. Here in Missouri, we do have some breccia, but our breccia more commonly occurs where pieces of rock on the top of a cave fall to the bottom of the cave and get glued back together. We call this cave breccia. And so, again, every rock is going to tell a story. One other type of sedimentary rock that we have around here is also made of gravel, but this is where the gravel is much more rounded. And if we take a look at this sample right here, you can see that the pieces are rounded, telling us that water was involved and rounded off these different surfaces. And so as a result, we have a piece of conglomerate. And this conglomerate is going to, again, high energy environment where maybe a river washed off these different materials, washed away the silts and the clays, and then what's left behind are bits of gravel that got buried. We can think of a river around here. We have a number of small creeks and streams that are washing fast enough to keep the sands and the silts away, but leave little bits of gravel on the ground. And this, as a result, will eventually lead to a conglomerate. If the water was moving a little bit slower, it's going to start to deposit out smaller bits of material. And in this case, we've got a couple of different types of sandstone. Arkose is a type of sandstone in your book, but this is where water is moving fast enough that it's going to deposit sands, but carry away the silts and the clays. And if we get this material that is, again, really close to its source, where you're going to end up with not you're breaking down these rocks, but you still have some clay or feldspars, which are haven't formed the chemical sedimentary rocks of clay. What you're going to be left with is a stuff called arkose sandstone. And again, it's going to have this bits of material of sand, primarily sand-sized particles, but it's going to have lots of different minerals in them. So here's an example of some of that arkose sandstone. Here's a local example of a bit of this sandstone that isn't made up of arkose material, of feldspars. It's almost all pure quartz. Now, this sandstone here is really, it's quite useful. This sandstone is actually mined up near Crystal City, where they were actually taking this very sandstone, pulling it out of the ground, throwing it into an oven, heating it up, and it's pure enough that it doesn't contain enough impurities, so you're going to end up with really pure quartz glass. And this is known as, well, this is why Crystal City has its name. This sand has also got some other uses these days. There's a company, Pacific Silica, in Pacific, Missouri, that is mining out this same sandstone. And this same sandstone is used, or that is being hauled off for what's called fracking sand, where they crush this up, throw this in the ground into a shale, and that shale during an explosion is going to actually these sand grains are going to prop up the pore spaces during that explosion and allow the oil to escape. This is a process known as fracking, and so it's very dependent on having a good sand-sized particle. If we get even smaller grains, we're not going to be able to see these grains, and then we have our siltstones, our shales, or mudstones, all of which are microscopic little bits of material. Now, siltstone does have the consistency of, say, baking flour, is a really good size particle of siltstone. It does have a very fine grain, but the silts in our siltstone are big enough that they're actually going to fall out of the water very easily. And so one of the ways to differentiate between siltstone and shale is the siltstone, when it's in water, it will precipitate out in just a few minutes. Materials that are smaller than silt are clay. And so mixing these materials around, they are so small that the surface of these materials are actually going to be attracted to the water molecule. We all know that a water has H2O. One side of the water has the oxygen, which is a much larger molecule. Then the other side is going to have, at a 104-degree angle, the two hydrogen molecules, and it kind of looks like Mickey Mouse. And so one side is going to have a positive side, one side is going to have a negative side through to so it's going to have, this is one of the reasons why water is a universal agent, dissolving agent, because it's going to have one side that has the two hydrogens and one side that's going to have the oxygen. So it's going to actually be able to pull positively charged ions or negatively charged ions. And these surfaces of clay tend to be negatively charged. So they're actually going to be attracted to the hydrogen side of the water. And so as a result, what's going to happen is it's actually going to slow the movement of this water as these clay particles as they sink through the water. This is the reason why clay particles are going to stay suspended so well in water. And if we start looking at these clay particles, the water has to be moving exceedingly slow for siltstones, shales, and mudstones. And so as a result, they're not going to lay perfectly flat. They're going to tend to break into flattish sheets. Now, when we start looking at shales, shales are going to, because they break into flat-ish sheets, because they lay in flat sheets, they're going to break apart into flat sheets. We have some shales around here that break into flat sheets. These clay particles are not very well compacted, and so you can actually break these samples apart. The technical name for these sedimentary rocks that break into flat sheets and break apart into flat sheets is called fissile. And so you can see, I don't want to get my keyboard too messy, but we can see that these rocks are breaking into flat sheets. All of these individual bits of rock are flat sheets, or fissile. As I mentioned, we can use the idea that transportation, moving these materials tend to cause some abrasion or some rounding of different grains. The further that they've moved down, the more rounded these samples will become. And so we can actually see what the conditions, the fluid that transported this material down, whether it be air or water, how long it's been since it's been rounded. One of the applications that we can use for this is if we're trying to figure out where the source of this material is. So if we saw this material, let's say that this piece of material was a bit of gold, and we want to know how far upstream do we have to go to try to find where the source of this gold came from. Well, if it was really, really well rounded, we would know it was traveled a little bit, or it traveled further than if it was very angular chunks. Also, when materials start to get deposited, if they became deposited very, very quickly, maybe by ice, where all of this material drops out at the same time, you're going to end up with a very, very poorly sorted materials. Ice tends to have very poorly sorted materials. Water is really, really effective at sorting out different sediments. As water starts to slow down, what's going to happen, it's going to deposit the big stuff first, smaller stuff, smaller stuff, smaller stuff. Yeah, and so as a result, the river deposited materials tend to be very well sorted. And I say well sorted, I mean everything is going to be the same size material. And so the more longer that sediment has been moved down, it's going to wash away any of this clay. And so if we have a mature sediment, it's going to contain very well-rounded materials, very, very uniform sized materials. So as I've already mentioned, lithification is a process of becoming a rock. Lithification can occur in a number of different ways. Anytime you take a bit of sediments that are going to become lithified, maybe with gluing or with just pressure contact materials. And so we've got a couple of different samples here where we have sediments that are becoming sedimentary rock. And so the first example looks like they have a bit of angular materials which became lithified to become a sedimentary rock of, looks like a piece of breccia there. Then we have some sands which became a sandstone. And so when we start looking at the middle image there, we have a desert where we have some winds blowing around. Looks like a lot of beach, of desert sand that got glued back together to form a sandstone. And then the muds were going to yield a shale. And again, please note that when you start looking at the shale tends to be breaking in those flat-ish sheets there, that fissile. So some of the other types of sedimentary rocks that you can form, formed not by clastic, not by the Rice Krispie treat style material, but more like the rock candy, where we have sediments in a solution, or ions in a solution that are precipitating out. And so there's three main categories of these. These can get a little bit blended because we can end up with the same type of rock through a couple of different mechanisms. So these can be biochemical, and some biochemical is using life. In the life process, you can take in different ions to secrete different types of shells. And as a result, these shells can get glued together to create things like limestone or chert. Then we have organic materials. Now, typically, when things die at the Earth's surface, microbes will break down these different materials. But if we have an environment that's a reduced environment, lacking oxygen, what can happen is the organic materials can get be left underwater, and what we end up with is this organic material just starts to pile up thicker and thicker. And again, if we're in like a swamp, there's no microbes that are going to be breaking down this material. It's just going to get thicker and thicker and thicker. And as a result, it's going to lead to these piles of organic material that we're going to, some examples of this would be coal. Now, sometimes you end up with some clay getting washed into this area, so you can end up with clay particles with mainly with a lot of organic material, and this is going to be called an organic shale. Organic material tends to be black, and so when we start looking at this reduced environment, these organic shales tend to have some blackish color in them. Some of these organic shales are highly sought after these days because that organic material we can actually try to recover some of that organic material in the form of oil or gas. Coal is also this organic material, and so we'll look at some of the different types of coal here in a second. Then we have some other chemical sedimentary rocks, the rock candy style, where you end up with organic material, or excuse me, we end up with ions, that those ions are going to precipitate out of the water. And some examples of this would be halite, where we had salt water and the water evaporated. And so what's going to be left behind is a sample of little piles of the mineral halite, and it's going to form this rock called rock salt. What I have here is a bit of gypsum that evaporated out of the water, and you'll recall gypsum is 2 on Mohs hardness scale, so I can even scratch this sample very, very easily with my fingernail. It's again softer than my fingernail. So when we start looking at these biochemical sedimentary rocks, biochemical is again using life to take the ions out of the water and make things like shells. And there's a couple of examples of here. The most common example of biochemical sedimentary rocks is a sample called limestone. Now, Missouri has a tremendous amount of limestone. We take a look, with the exception of the sedimentary rocks, with the exception of the igneous rocks in the southeast part of the state in the St. Francis Mountains, a lot of the rock surrounding this area is a lot of this limestone. One of the ways to identify a limestone very, very easily is looking at finding the calcite in that. Now, as you recall, calcite reacts with an acid, and so as a result, through organic material creating carbonic acid in the groundwater, you can dissolve some of this limestone. As a result, we end up with sinkholes and caves. Missouri is known as the cave state because of the abundance of limestone, which ultimately led to these cavities. If we take a look at some samples around here, this is a sample that has a number of different little bits of organic of little shells. And so this is not an uncommon photograph of rocks around here where these limestone platforms of organic shell material became larger and larger and larger. Now, as this is a liquid environment, the material may actually start to get broken down into smaller bits, and so you may end up with little bits of clay dust or shell dust. And so as a result, you may end up not being able to see the actual fossils of these shells. Again, some of these are very, very microscopic, but they're still there. They're still going to react with acid. And here's my acid. And if we take a look at this sample here, I'm going to try not to. You can see, and in some cases even here, that sample is fizzing as it's reacting with this acid. Anytime you take an acid plus a base, you can actually neutralize that acid and dissolve this, in this case, dissolve this rock. Missouri is known for the abundance of this calcite. I think I've mentioned that you can use this limestone. If your stomach is too acidic, what you can do is you can actually take this limestone and eat it. Now that may seem very disgusting, but there's a little bit easier method, and that would be taking some Tums. So that can, the one with calcium, it can start to dissolve, neutralize the acid and improve the way you're feeling. Now, another type of biochemical material is instead of using the ions to create calcite, and our bones are effectively very, very, very similar to calcite. So if we had a bunch of organic material from left behind by bony fragments, we could end up with a limestone in that case. The other thing that you could end up with is if you had some really cold environments, or if there's not enough calcite to create, or enough calcium, carbon, and oxygen in the water, some organisms can create shells out of silica and oxygen. And so as a result, we call the silicon oxygen tetrahedrons quartz. And you can actually use life to create this silica secreting sediments to create chert. And so you can, in fact, have samples of chert. You'll remember that chert is, quartz is 7 on Mohs hardness scale, and it doesn't react with acid. So if you had a sample that had biochemical chert, it would still have those organisms, and you would be able to, under a microscope, see these microscopic little organisms, but they wouldn't react with acid. Then we have some organic sedimentary rocks, and I've already mentioned organic materials are normally broken down at the Earth's surface, but in the right environments, reduced environments, they can accumulate to create these things called coal. And so this coal, again, organic materials that are partially decomposed or not decomposed at all are going to tend to have this blackish color. And so we have this example of a little bit of coal at the Earth's surface. Now, the United States as a whole have some really, really high concentrations of coal. We have, I've heard upwards of 500 years worth of coal burning at the current rate. Some other organic sedimentary rocks which can occur as kind of a blend of the chemical sedimentary rock of, classic sedimentary rock of muds, and some of the organic material, and this can create things called oil shales. When we start looking at chemical sedimentary rocks through some non-life organism or some non-life mechanism, which are going to create these rock candy-like structures, or rock candy-like sedimentary rocks. And so the classic example of this is halite, which again is going to create rock salt. As we know, salt will dissolve in the presence of water. So in order to have these evaporites starting to form, you need arid-like conditions, very, very high desert-like conditions. Because if you had too much water, it would just dissolve again. We have gypsum. Gypsum, as I already mentioned. This gypsum is also in an arid environment, but it has some different ingredients in here compared to the calcite. And then finally, we have a material called travertine. Well, travertine is commonly associated with when we have calcite dissolved in the water, and then the water changes temperature very, very quickly. Some of the best examples of travertine deposits that you may see and be familiar with is if you go to places like Yellowstone, where you have this dissolved water, very high temperature, cooling off very quickly, depositing its material in travertine. And so travertine is a white mineral primarily, but if we start looking at the travertine deposits in Yellowstone, these travertine deposits, because the water is changing temperature so much and you have this hot water influx coming in, you have some extremophiles, some organisms that really love this hot water, and they will produce these very brilliant multicolored organisms in Yellowstone. And then finally, we have replacement chert, where we have some either limestone, where the groundwater passing through can replace some of this calcite with quartz. And so what's going to be left behind is a piece of chert, a chert nodule. Now around here, we have lots and lots and lots of dissolved chert in our water. In some cases, that water evaporated and allowed the crystals to actually show their euhedric, show their shapes. And so as a result, we end up with little tiny quartz crystals kind of poking out out of the rock, and so we call this druzy quartz. Technically, it would be a chemical sedimentary rock. So as I've already mentioned, the evaporites are evaporating out of water, and so halite, which we know is table salt, and gypsum, which is drywall, are also precipitating out of these environments. If we wanted to see an environment where we actually see these evaporites occurring right now, we could actually watch this occurring in the Great Salt Lake. We could see this in the Dead Sea. One of the other places that we have seen this is when we've dammed up rivers and create these huge bodies of water behind the rivers. The water evaporates, leaving behind a salt residue, a white residue around places like Lake Mead in the western part of the United States. So here's some of these travertine deposits. Another place that you can end up with this travertine deposits is in caves, where the water evaporates, leaving behind this dissolved, the mineral of calcite. So here's some of the replacement chert, and where we have limestone, where the silica is replacing some of the chert. Around here in Missouri, we have lots of examples of this limestone. As the rivers are cutting through, they're going to very easily dissolve the limestone, but these cherts, again, are made of quartz, not easily chemically weathered. So as a result, what's going to happen is if we had these chert nodules, like we have in this example here, and this limestone washes away, what's going to be left behind are these cherts. And so these cherts are going to end up in the rivers, and you can see right by this guy's feet, there's a bunch of chert nodules that have washed out. And so this is why, if we want to see a bunch of chert, it's very, very common to see these cherts in these rivers. I went floating this summer with my family, and my son was really, really excited about trying to identify some samples. And I felt so bad because he found so many of these different samples. They all kind of looked a little different, but they were all bits of chert. Again, chert is made of quartz. Quartz can have any color of the rainbow. And so he found these brown samples and these more white samples and some of these more reddish samples, but they were all examples of chert with some varying amounts of iron tainting. So you can end up, so he found these these samples, and he was so excited to find these samples and wanted to have a rock collection and wanted to have lots of different samples, but they were all in fact, bits of chert. So not only can we identify these rocks based on what type of environment did they form, example, coals are formed in swamps, and quartz sandstone is found in river deposits where the water has been moved and removed all those clays. But they can also tell us that we can have these things called sedimentary structures, which we know that sedimentary rocks are going to fill in any low-lying regions. So if we end up with new sediments being deposited, they're going to be deposited as horizontal layers that we call beds or strata. And so the bedding or stratification can tell us a little bit about the environment in which these materials were placed. If these materials are constantly moving, what can happen is you can end up with some very distinct bedding structures. And so some classic bedding structures that your book is showing us here is these different layers of sedimentary rock that are standard beds. A lot of times you'll see these on road cuts because they cut the road to make a nice flat surface. And so as a result, all these different beds, these different layers are easily exposed, and we're getting some differentiation of weathering to really expose these different features over here. Another sedimentary structure as a result of moving wind or water are ripple marks. These ripple marks are going to tell us which direction the water was moving. And so creating these ripples. This is very important if geologists were trying to reconstruct where the water was coming from, what direction we would expect to see different materials. So we'd expect to see clays further away from this area in that same time environment, and maybe some more beach deposits further upstream, further up the waves. And then finally, we have cross-bedded samples. Cross-bedded samples are associated with dune development, and I don't know how well this is showing up on this image here, but these these waters or winds piling up are going to cause these dunes to continuously push this material up, and then you're going to end up with some falling that is taking place in this area, creating these cross-bedded materials. If you'd like to see some of these cross-bedding and don't want to have to go out to Utah to the Navajo sandstone, which is what was in the image here, you can go to Pickle Springs and see some of this cross-bedded sandstone locally. If we had an underwater landslide, what's going to happen is the heavy stuff is going to drop out significantly faster than the silts and clays. And so what's going to happen is this pile of sands are going to form, then silts, and then clays. And then if we had another turbidity current, then you're going to end up with another pile of sand, silt, and clay. And as it turns out, this is very, very useful because sometimes on occasion, we can go to look at the Appalachian Mountains and places like that where the rocks are tilted and no longer horizontal. And as a result, we can figure out which end is up, which direction was up, which should these rocks get tilted this way or this way under formation. If we're starting to see this graded bedding with this big stuff grading to fine, that big stuff grading to fine, I know that the rock was tilted in this direction. Another way that we can figure out which end is up is by looking at things like mud cracks. Now, when we have mud drying out, the top is going to dry out more than the rocks underneath. And so as a result, these mud cracks are going to open up. We can get some infilling that has occurred on these in these cracks. And so when this rock actually lithifies, we can actually see which direction which way is up again with these mud cracks. So when we start looking at these rocks, we see that there's lots and lots of different depositional environments. And so I'd encourage you to look at these different depositional environments here. And so we can see what type of sediments are associated with these layers. And so each one of these are going to create a different pile of sediments, different type of sedimentary rocks. Some non-marine glacial sediments are one of the few places that are not washing materials down under sea level are things like glaciers. Now, glaciers are really, really good at picking up bits of rock and mixing them all together and then dumping them all at the same time. And we call this material, which has big stuff and small stuff all in the same area, is called till. And so if we had a environment like a lake or a river, these are areas that are going to deposit materials above sea level. By and large, a lot of these images, we can see that this material are being washed down to the sea. And so there are most of the sedimentary rocks are going to be found in below sea level, since materials wash from high areas to low. Some other non-marine deposits of materials here, some reworked materials associated with this gravel bar. As this river is washing this material away, it's cutting away at this bank, but it's depositing material right here. Here's an alluvial fan. It's kind of we have a very similar to a delta, which we're going to talk about in a later chapter. But this alluvial fan looked like one of those old-timey fans that where the river or the valley of sediment washed down, and then what happened is it found the path of least resistance. So it's going to go in lots of different areas in this location. And so when we start looking at the vast majority of sedimentary rocks are going to be these marine deposits, marine ocean deposited materials, these coastal environments. And so some classic examples of this are these deltas. And we can actually see these deltas start to separate out. The stuff near shore is going to be more larger grains like sands and in some cases gravels. You get further away from the river, you're going to end up with silts and clays. And if you had warm, shallow, clear marine waters, you can start to create these carbonate reefs, these limestone deposits. Now, as I just got done mentioning, Missouri is covered with a bunch of this limestone. And so what this tells us is we, at one time, with the exception of the St. Francis Mountains here, the rest of the state was covered by warm, shallow, clear marine waters. How do I know that? Because I can see the limestone there. And again, every rock is telling a story. These deep marine warm, shallow, clear marine organisms are telling us we have things called plankton. And these planktons can be extremely, almost all calcite. And so here's a microscopic view of these little bits of plankton. And there is some organic material in here that can be left behind. So if we buried this material, any of that organic material, this would be a potential for a good oil trap. But one of the other things, if the organic material has left, what you're going to be left behind is this stuff called chert or chalk. Chert being silica-rich materials, chalk being the calcite-rich materials. One of the other areas that you can end up depositing materials is in basins, which are low-lying areas, and there's lots of different types of low-lying environments that are going to create traps for sediments. If we have a foreland basin, if we had, say, if we look to the left of this image, maybe we had a subduction zone, creating a big mountain range here. And so some of this material is going to wash off back into the ocean, but some of that material is going to wash in this direction and start to deposit this material to create a four-arc basin. If we start pulling rocks apart, like the Rio Grande Rift area or the African Rift Zone, what's going to happen is as these rocks are pulling apart, some of this down-thrown areas are going to create traps for this sediment. If we start looking at the southwest part of the United States, the Basin and Range region, and we have some of these rifted areas. If we end up with a low-lying area in the continent, it can start to cause this area to build up in sediments, and it can actually cause this material to start to sag. A great example of this would be the Illinois Basin, where all this piles of sediments in Illinois. And then we have areas like the eastern coast of the United States, where we end up with a passive margin. As you recall, a passive margin is a region that is not on a plate boundary. So you have the land switching over to the water, and again, land continental crust is much thicker. And so as a result, what's going to happen is it's going to create this passive margin where the sediment is starting to build up. So one of the other things that we're going to be talking about is gradual change over time. As it turns out, sea levels can rise and fall, and as a result, the interface, that coastline where sediments are being deposited, can move further away from its current location, or the seas can rise and cause the land to get smaller. And we call these terms transgression and regression. So if we are, if the land is rising or sea level is dropping, then we're going to call this a regression of the sea. And if we have sea level rising and the land retreating, then we're going to call that a transgression. And over time, we can have the layer of rock that is being deposited moving offshore or further back. There's a nice video of this in the PowerPoint's presentation, also in the textbooks student videos located in the same area that SmartWorks web page is. So I'd encourage you to look at that. It's a great visualization. The last 2 times I've had problems with my visualization on the PowerPoint, so just go to that site instead of me trying to play it and stream it, and there's a lot more lag there. Same thing with this soil formation video. The soil formation video is a great way of visualizing what's happening when we start looking at soils. Now, soils are different than sediments in that soils contain organic material, mainly bits of rock and sediment, but also the organic material as well as air and water. And so when we start looking at soil, it contains that organic material as well. Now, when we start looking at weathering, which we've already talked about this chapter, breaking down the bits of rock into smaller bits, then what can happen is groundwater can start to move this material down and incorporate some organic material. And so as rainwater is starting to wash some of this organic material down, this area at the top is going to have a lot more organic material in it. We mentioned that clays are really, really small, and so they can actually remain in the groundwater and start to precipitate out further downhill. And they're trying to show that here with those little lines, those little white lines are bits of clays. So the oversimplified view of soil is going to have organic material, this topsoil, which we used to call just the A horizon. Then we had the subsoil, and then we had weathered bits of bedrock. But as it turns out, we can get much more specific when we start looking at this soil, that the topsoil really does contain a lot of organic material at the top. So we actually have a separate subsoil, or a separate soil layer or horizon, telling us that we have The O horizon is rich in organic material. The A horizon, rich in organic material, but a lot more minerals. This transition zone E is what's happening is we've gotten rid of a lot of the organic material, but some of the clays have washed down. And then what we have beneath that is the subsoil, where all those clays are starting to develop. And you'll see that the reason why it's called a horizon is because it is layers. And these are going to be very, very dependent on climate. The more rain you have, obviously the more washing of this material down. And so there, if we start looking at these soils in the past, they can tell us what the environment was like. And so we've got a couple of different types of soils here. There's when we start looking at these different soil types, the first type of soil that we're going to be looking at is a desert soil. If we start looking at this desert soil here, we don't get much rain. And so as a result, that the O horizons are pretty non-existent. But what's going to happen is when we do end up with rain, it's going to wash some of the sediment or some of those dissolved minerals down, but then the water evaporates. And so what's going to be left with is this pile of organic of dissolved minerals, and usually this is a mineral called calcite. As the water evaporates, so you're going to end up with a layer of calcite called caliche. You may be familiar with this caliche if you've live in places like Bonne Terre, which are really hard water. What it's hard with is this dissolved calcite. And as it turns out, this calcite precipitating out is going to be piles of chemical sedimentary rock of caliche. If we have an area that has a little bit more rainfall, say around here, we're going to end up with some alpha sols. We also have some mollisols to the north of us, but we're going to focus on these alpha sols, which are rich in Al, aluminum, F for ferrium or iron, and these are very common in chemically as products of chemical weathering. And so as a result, what you're going to end up with is a typical soil profile is going to have organic material, this subsoil of A horizon. We may end up with a little bit of that transition where we've removed the organic material and left behind little bits of silts and clays. Beneath that, all those clays are accumulated in that zone of accumulation in that B horizon, and beneath that is the weathered bits of rock. And as the weathering is occurring down at the bottom, what's going to happen is those clays are going to get further down. So this entire area is getting moved down. If we live in a tropical environment, you're going to have lots of chemical weathering taking place because warm, wet environments are really going to speed up those chemical weathering processes that we talked about earlier this chapter. As the weathering is occurring, it's going to create these really, really deep, thick soils. These are called oxisols, oxidation sol-rich soils. As it turns out, these oxisols this chemical weathering rich are actually going to be very, very effective at making soils that are really rich in aluminum. As it turns out, we can actually process this aluminum. This is where our aluminum is coming from. We need these oxisols to really separate out the organic, to make it commercially viable to create aluminum by taking these aluminum rich soil layer, and one of the minerals that are very common or mineral families is called bauxite, and it just looks like an old weathered bit of rock, and as a result, it's going to we can process that aluminum. So here are the class questions. Again, these are also found in MyMac in all the ancillary PowerPoint materials. So I'm just going to quickly go through this.